In our qualitative and quantitative experiment, we had two different parts. One was looking at properties of substances to identify an unknown, and the other was determining a quantity, the number of water molecules in a hydrate, in a salt hydrate. So let's consider that first part, chemical and physical and changes and indications of a chemical reaction. So the difference between a chemical change and a physical change is that in a physical change, the substance keeps its identity. And so it's still the same substance. For example, any phase change is a physical change. And so it could be melting, freezing, vaporizing, sublimating, any phase change like that. Also, you may not realize that dissolving is a physical change. You maintain the type of substance. Anyway, so those are examples of physical changes. For chemical changes, you get new substances. So combustion or burning is a chemical change. Rusting, you're getting new compounds being formed. Rotting are all some common chemical changes. The other thing you need to know is the indications that a chemical reaction is occurring, and we use these again later in another experiment as well. But the first one is that you see a precipitate form. That's when you have two clear solutions and they get cloudy because of little specks of solids that form. A color change. A mass change. And a mass can change because of a gaseous product or reactant coming and going. It may not be obvious that it's coming and going, but it can cause a mass change. And last one is a gas forms. So if you see bubbles or something like that, it's a sign that you have a chemical reaction. The other part of our experiment involved a salt hydrate. And so a salt is an ionic compound like this copper-2 nitrate. And a hydrate basically has water molecules that are attached in a regular pattern as part of the crystal structure. And so for us, we want to determine this X. We want to know how many water molecules per unit of copper-2 nitrate there are. So that was our goal. An empirical formula would be this, but with a number in place of that. So what we did, and I'm going to just kind of draw like ours were, we had bright blue crystals, just to remind you, and we did 2 flasks, not just one, but I'll show you with the one. We put the crystals in our flask, and then we heated it on our hot plate. And when we heated it, the water that was part of the salt hydrate escaped. Okay, so what we did was we weighed it before we heated it and we weighed it after, and then we knew how much water escaped. We could figure out how many moles of water that was and then compare it to how much salt was left, and that would give us our ratio to get this X. So let's just mark a few things in here. So you're always starting with the hydrated form of the salt. The idea here is that you're looking for, I wrote an X up there, but it's this Y here. This X will be a 1, so you won't worry about that number. And we'll always have the mass before and after. It loses mass during heating. The mass that it's losing, again, you're starting with the salt hydrate. You're heating it. After you heat it, you have the anhydrous salt. And what left was the water. Okay, so how much water was lost? Well, that's easy. Just look at the mass before you heated it. And subtract the mass that it had after you drove out all the water. Okay. Okay, and then we need to convert that to moles because that number that we're looking for, this X, is in terms of moles. So we need to convert this grams to moles. And we do that using the molar mass of water. Now I wrote down some extra digits. There should be only 3 sig figs, but in this case it is good to kind of have some extra digits. You may don't write them down as an answer, but have them on your paper so that when you go to the mole ratio it comes out a little nicer. Okay, so that's how many moles of water left. How many moles of anhydrous salt were in there afterwards? So the anhydrous salt is this. It's the mass after heating. Okay, so the mass after heating. And we're trying to get to moles, so I need a molar mass. And that may be given to you, or you may have to calculate it by adding up on the periodic table. Okay, and so the grams go down here. And again, on sig figs, I guess I need, I really only have that many, but I'm carrying extra digits. Okay, now we have a mole to mole ratio between the salt and the water. And so we're using these two numbers, but we need to get a whole number. So to do that, what you do is you divide by the smaller of the two. Divide them both by the smaller of the two. And the smaller of the two is this one here. So I'll divide them both by that. And at this point, on the lab ones, because we don't have a number in the front, and the number in the front is a 1, so here you'll round to a whole number. And since it's 3 to 1, that means that my empirical formula is the formula of my salt. Then I have a raised dot 3H2O, because there are 3 moles of water for every mole of the copper 2 nitrate. Okay, last thing, what is the name? What do I call that? So you take the name of the salt, and then since it had 3 waters, we'll say try and then hydrate. So I can get both the formula and the name.